Electric fields then, if you've been following through the series of lessons that I've been doing, you've already looked at gravitational fields with me, and some of what I will say just now will repeat what I said at the start of the gravitational field section. But just a reminder that at this stage of the course, you will have almost certainly done circular motion and simple harmonic motion, and those bits of physics are used extensively in questions with electric fields, gravitational fields, and magnetic fields. So you need to pull that together with this work in order to be successful ultimately with the questions on fields. So let's define a few terms then. What is an electric field? If you remember from the work that you have done on gravitational fields, if you've covered that, you will know that a field is a region where something experiences a force. Note region, not area or place. It's three-dimensional, it's a volume, it's a region. So this is a region where, let me make that a bit thicker. It's a region where charge experiences force. So gravitational field is a region where mass experiences force. An electric field is a region where charge experiences force, and the corollary of that is that charge is that which experiences a force in an electric field. And magnetic fields, well, they're a bit different. They are a region where moving charge experiences a force. More of that when we come to that section of the course. So field strength, if you've done gravitational fields, you'll remember that the gravitational field strength at a point in the field is the force on 1 kilogram placed at that point. This is, if we just at a point in the field. The field strength is the force on, well, we said 1 kilogram for gravitational fields. We have to define the sign of the force or the charge here. So we're going to take positive charge plus 1 coulombs placed at the point. So field strength is the force per unit charge, newtons per coulomb. So that's what a field is. Generally what an electric field is specifically, that's what we mean by field strength. And I've compared that and contrasted it to gravitational field strength because with gravitational fields we don't have negative mass, and so we don't have to talk about plus 1 kilograms. It is 1 kilogram. But with charge we have both positive and negative charge, and so we have to define what we mean by the charge, the unit charge, because force is a vector, it has a direction, and so if we don't say the field strength is the force on plus 1 coulombs, then we're being a bit vague. We could have said minus 1 coulombs, but the convention was plus. So that is the definition then of field strength in an electric field. Now, one of the things you need to be able to do is to compare and contrast gravitational and electric fields. That's why they're very often taught together. Now, this is one of the differences in that you have to define your field strength as the force on plus 1 coulombs. But one of the really big differences is that the gravitational field is never truly uniform. We talk about the gravitational field close to the surface of the Earth, for example, as being uniform. It's approximately uniform, but it isn't actually uniform. Gravitational fields are radial. So here we have a field strength which is inversely proportional to the square of the distance from the charge, and here uniform means not changing. The field strength is constant. Now, one of the differences between gravitational and electric fields is that electric fields can be uniform, whereas gravitational fields cannot be truly uniform, but we do talk about a gravitational field close to the surface of the planet being uniform, because if you remember, if you were to draw your field lines around your your mass, you would have field lines that look like that. Approximately. These are supposed to be radial. My apologies that they're not quite radial. So they would be pointing in towards the mass, because gravitational fields are always attractive, remember. But you can see, and maybe not here, but you can see here that the further away you go from the surface of the planet, the further away the field lines are from each other, and that indicates the strength of the field. So as you go out in this direction, the field gets weaker because the field lines are getting further apart. Whereas with a uniform field, and we'll see this in a moment or two, you have field lines which are parallel. I know that's not very parallel, but the diagram I'll draw later will be better. So here the distance between the field lines is not changing, and so the field strength is the same all the way down here. The field strength here, and the field strength here, and here, and here, and here, and here, all the same. So this is a uniform field. The field lines are parallel. There's no changing distance between them, so the field strength is constant. Whereas here, ignore these because these are rather poor. Here you can see as you move away from the surface of this mass, the field lines are getting further apart, and so the field is getting weaker. And it's a 1/r squared relationship. Again, if you've done the gravitational fields, you'll remember that, I hope. So there's what a field is, what an electric field is, the definition of electric field strength, the two types of fields, how that compares to gravitational fields, in that gravitational fields are always strictly radial. We do talk about approximately uniform fields, but they're not truly uniform, whereas with electric fields you can have genuinely both radial and uniform fields. One of the other differences, of course, is that because you have both positive and negative charges, then you can have attractive fields between positive and negative, but you can also have repulsive fields between two positives or two negatives. You do not ever have repulsive gravitational fields. They're always attractive. So there's another one of your differences. So let's move on then from that. So that's our introduction. Let's then look at some field patterns. Now these will look familiar to you. Here we have an isolated negative charge, and if you looked at my video for gravitational fields, that's exactly the same diagram I drew for an isolated mass. Exactly the same. So there you have an isolated negative charge. Remember, we said that the field strength was the force on +1 coulombs. This is a negative charge, and so your positive +1 or any positive charge would be attracted towards this, and so the field lines are coming in towards the negative charge. But if we had an isolated positive charge, well, that looks like this, because if I put a positive charge here, it would be repelled from this positive charge. So the field diagram for an isolated negative charge is just the same as the field diagram for a mass in a gravitational field. But we have this positive charge where the field lines are coming out from it. You don't see that in gravitation at all. And I have done a different number of field lines around this just to remind you that the density of the field lines, flux density if you like, the density of the field lines indicates the strength of the field. So these would be fields of different strengths, but also different signs, because this one is attractive and this one is repulsive. So there you have your field patterns around two isolated charges, either negative or positive. Notice that the lines, the field lines, are radii of this circle. Notice that with the positive charge, they're going away from it because the force is repulsive on our test charge, r +1 coulombs, whereas here they're coming in towards it because if we put +1 coulombs here, it will be attracted towards the negative charge. So those are the things to remember about those diagrams. So let's look at the field around two spheres. So let's say we've got two positive charges. Now let's start with two negative charges. So if these are negative, remember the field lines are becoming in towards the charges, but these two themselves would be repelling. And so if this is fixed in this position, this is fixed in this position, what you would get then in the middle here, if these two are the same magnitude of charge, bang in the middle, you'd have your neutral point where there is no net field. The field due to this one is exactly cancelling the field due to this one at this point. So you can see how out here the field from this one is not affecting this one, so it's just like it was before. But the field lines here are curving. Remember, field lines never touch and they never cross. And in the middle here you would have your neutral point. So there you have the field pattern, or an example of a field pattern around two negative charges. So if we had two positive charges, it might look exactly the same, except the lines are going the other way. So there you have the pattern around two spheres, both equally positively charged. Obviously, if one is a bigger charge than the other, then your neutral point is shoved towards the weaker one. And you can, using the law we come up with later, work out where that neutral point is along the common line of centres. So let's then look at the field lines between two spheres of opposite charges. So here we have a positive sphere on the left, a negative sphere on the right, and your field lines would look like this, going from positive to negative, starting out radially at the surface of the sphere and curving. And out here, of course, the sphere is really having no effect. Likewise, out here, this sphere is having no effect, this charge. So there you have the field pattern around two opposite spheres. And the field lines, the path taken by positive charge placed in the field would go from positive to negative. Let's look then at uniform fields. Having looked at the field patterns around spheres isolated and spheres together, let's look at uniform fields then. So here we have two parallel conductors. The bottom one I have chosen to be earthed, 0 volts. The top one then is at plus V volts. So I've done it like this rather than drawing my power supply out here with my battery, just to make the diagram a little clearer. But the top plate is connected to the positive terminal of my power supply, the bottom plate connected to my negative terminal. And so I have plus V volts between these plates. And if I drew in my field lines, they would look like this. So in from the edges, this is an important point, in from the edges of the plates, the field lines are straight and parallel, and although I've messed this up a little bit, they are the same distance apart. So all in here, the field in this region here, the field is constant. It's the same everywhere. The same force on a given charge placed in the field. Again, notice it goes from positive to negative. At the edges then, the field lines curve. You can think about this path as the vector sum of the repulsion from the top plate and the attraction to the bottom plate. And when you add the two forces together vectorially, you get this path, depending on the position that you put your test charge in. So there you have the field pattern between two parallel conductors with a potential difference between them. Important points: straight lines away from the edges, from positive to negative, arrows on the lines, same distance apart throughout. Then at the edges, the field lines curve.